This is a lecture from OpenTuition. To benefit from the lecture, you should download the free lecture notes from opentuition.com.
Misuse of quantitative data, or as I call it here, the misuse of statistics. And we'll look at it in these headings: what to measure, sampling and the problem of small samples, the distorting effect of using the mean as an average, or the potential distortions that can come into that, false positives and false negatives, correlation, and the use of graphs or pictograms perhaps to give misleading impressions. So let's think first of all what to measure. And this is maybe the first place in which errors or distortions or deliberate attempts to mislead can come in. For example, you are wanting to you want a particular project to be adopted. So what you maybe show is that the internal rate of return of that project is rather higher than the alternative project, and you stay quiet about the net present value, even though the net present value of the project you're not really for is far higher. And really, if you're dealing with mutually exclusive projects, you should be judging it on the net present value. So that is picking a wrong measurement, really an inappropriate measurement to make your case. Absolute versus relative. If I say the risk of getting a disease doubles if you eat a particular type of vegetable, for example, then the chances are you will shun that particular type of vegetable. But you could be doubling the rate of disease, from 1 in 40 million to 1 in 20 million. And really most people will be quite happy to eat a particular type of food if the chance of becoming ill from it is only 1 in 20 million. So the absolute risk is very low, but the relative change in the risk appears to be very high. And then maybe this is how you phrase a question. So if you phrase questions in a survey, for example, would you like more money to be spent on the National Health Service? Most people will say yes. If you ask the question, would you like your income tax to be put up so that more money can be spent on the National Health Service, then I suspect the proportion of people saying yes is going to be falling a little bit. And if you simply said, do you want your taxes to be put up, then I think the proportion of people saying yes is going to be reduced very, very dramatically. So how you phrase the questions to people, whether you expect maybe the answer yes or no coming out of it, again can influence the way people respond and the inferences that you might be able to or be trying to get people to draw from the statistics which are being presented. Second one we can look at is this tyranny of small samples. So let's say we look at a sample of 12 people. We ask 12 people if eating a new breakfast cereal makes them feel more alive during the day. And let's say the chance of the breakfast cereal making you feel livelier during the day is about 50-50. If you're only asking 12 people, then there's a very good chance that maybe 8 out of the 4 will say, yes, it does make them feel livelier during the day. Because it's only a very small sample. It's like tossing a coin 12 times. You'd expect the answer to be kind of 6-6. But you're not going to be very surprised if the answer, instead of being 6-6, comes out to be 8-4, or comes out to be 7-5. Because you know that over the very small sample of only 12, there's a chance of this kind of statistical distortion, if I want to call it that, coming out. If you were to ask 100 people, do you feel livelier during the day because of this breakfast cereal, and you got the answer 75% of people say yes, 25% of people say no, you might go on to something. That it might be a bit like tossing a coin 100 times and finding that 75 times out of 100 it comes out heads. That's much less likely than tossing it 10 times and finding a 7-3 or even maybe an 8-2 break in it. And also, of course, the small samples are easy, quick and cheap to run. You ask 12 people, what do you think of the breakfast cereal? You don't get a very good answer coming out of them. You ask another 12. And you keep on going at these small, cheap, fast surveys until you eventually find 12 people, 10 of whom swear blind that the new breakfast cereal perks them up for the day. It's also possible with small samples to read too much into the results which come out. It's very easy to see patterns where none exist. So here, and this is in the really taken from the notes as well here. Here I want you to imagine you've got a country which is 100 kilometers, 100 kilometers up and down and 100 kilometers the other way. And what we have is a railway line, or maybe a high voltage power line going through the country like that. And what we're looking for is incidence of a disease happening. And it's a very rare disease happening. And in the country, every year, there are only 4 people who fall ill from this disease. Now, what I've done here is I've selected these points at random. It's done through a kind of Excel program and plotted on the graph. And you see, I didn't have to rerun the model very often. Before I got it kind of coming up here we have got, sorry about that. Here we have got a person in here, we have another person in here, one in here, and so on. These people seem to be almost exactly lined up under the high voltage power line. And it's very easy to be seduced into thinking, well, there must be some connection between the high voltage power line and these people. It would be just as easy, to end up with your 4 people kind of over there and so on. But if we magnify this country up a little bit, and we make it kind of 10 times bigger, then over one stretch or other of this power line, you will see, what looks like a pattern of people, a cluster of people, who are falling ill, who just happen to be near the power line. But there's no cause and effect on this. It is just a random distribution. But if you're only dealing with 4 people, sometimes they will happen to line up very close to what looks like a particular pattern. Averages and means. Again, is taken from the notes. So what we have here is an income distribution. Here we have the people in the population going up through here. So 10 plus 20, 30, another 30, 60, 100. I think it's 250 people in there. And it is an absolutely symmetrical distribution. 15, add on 10, 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 etc., etc. The mean of this is going to come out, and it does come out, at 55. So the mean or average wage or income of the population is 55. And if you had a wage of 55, you would feel, I'm pretty kind of happy about it. And I suppose half of these people are going to feel happy, half are going to feel, oh, I need to try harder and get my wages up and so on. But you take 55 as your benchmark. Now what we're going to do is we're going to introduce one more individual who has got a very high income here, coming in, I think, with 10 million here. And now we work out the arithmetic mean. It's 55,400. So now, if you are still on your income of 55, you're going to feel a bit hard done by. Here, most people have a wage which is under the mean. That sounds contradictory. That most people have income which is less than the average income. But it is distorted by this very high wage up here. And furthermore, the government could claim between this year and this year, average wages have risen by 55,400, whereas actually all that's happened is that this rich person has moved into the country and is distorting the reported average income of people, so that it looks as though it's improving. So means, if you're taking mean as a measure, can easily be reported by the very extreme values. it might be better in such a case to look at what's called the median value. The median value is if we've got 251 people here, I think it is, you count up here until you get to the 251st person, which is presumably in there somewhere, and you see, I beg your pardon, half of that, 251 would be about 125 people. You see what is the 125th, 126th person, the middle in the ranking actually earn, and that will still be around 55. It's not going to be distorted by this extreme value which you have out here. So for some measures, median is going to be better than the average, or rather than the arithmetic mean. False positives and false negatives can be very subtle and actually can be quite alarming sometimes. This makes use of something called Bayes' theorem. Don't worry about it too much. Anyway, let's say that 5% of the population we know has a disease. And there is a diagnostic test. And if this comes out saying that you have the disease, in other words, a positive result, then there's a 90% chance it is accurate. But on 10% of all occasions, it gives what's called false positive readings. It says you have the disease, but in fact you don't. If the diagnostic test says you don't have the disease, that you are negative, then there's an 80% chance that it is accurate, but there's 20% chance that even though the test says you don't have the disease, you actually have it. That's what's called a false negative. Now, let's say you go for this test and you're told the test is positive. You go away thinking, well, there's a 90% chance, there's a 90% chance, therefore, I have the disease because, there's a 90% chance that it is accurate if it's a positive result. But this is far, far, far from the truth, actually. So let's build up a little table. This is by far the best way of dealing with this kind of false positive, false negative. See, here's a population, let's take it 10,000. We know that 5% of those, so it's going to be 500, really do suffer from the lurgy, this particular disease. And the rest of the people, 95%, do not. They are definitely negative. So what we do is we know that we have these people here who are have the disease in here, and we know from this that if the result is positive, then 90% of them have the disease. So here we have our positive test results coming out from these 500 people, and 90%, 90 times 450, have the disease, but the other 10% do not. Okay? So of the people who should be reporting positive, the test result only discovers 90% of them and misses the other 10%. Similarly, if you really don't have the disease, and a perfect diagnostic test would report that none of this 9,500 has a disease, it's actually only going to report 80%. So if you take 9,500 times 0.8 there, you've got 7,600. So this 7,600, that is your 80% times your 9,500. So if it was perfect, all 9,500 would come out with a negative test result, and you'd have 0 in the other one. But the test is not perfect. It only reports properly an 80%. It misses or misreports, shall we say, the other people. Now, you come out, therefore, you know you have a positive result here. So all the positive results here are that. Now, out of the 10,000 population, you're one of these people. You get a positive result here. But essentially, 1,900 do not suffer from the disease, and 450 do. So the actual test is saying that your chance of actually suffering from this lurgy, out of all the positive results, it's 450 out of 2350 in there. So the chance of you actually having disease is 450 divided by 2350. It's about 19%. A far cry from what it looked like originally, which was 90%. So these false positive, false negatives, where you have diagnostic tests, and it doesn't have to be diseases, it could be looking at the quality of products being produced, whether it passes and fails and so on there. What is the chance that a product, if comes out as supposedly a good product, actually is a good product if the diagnostic test is not correct and 100% accurate at picking up the risk of failure? And then we have the misuse of statistics and regression here. Here I think you can just about see the two lines here. What I've done is picked up real information from the internet. I've got 4 years in here, and I've picked up the incidence of diabetes in the UK in millions of people. I've also picked up the sales of smartphones in the UK. I think you just see this blue line in here. And you will see, I think, that there is a remarkable kind of, I suppose you would call it, correlation between these. And in fact, if you work out the correlation between these two effects here, it's of about 0.99. It looks as though the movement of smartphone ownership and the movement of diabetes are absolutely linked together. Now, of course, no one in their right mind is going to think that owning a smartphone is going to cause diabetes, but we've got two variables which just happen to be moving together, and a non-scrupulous person could try to use this correlation to demonstrate that owning smartphones causes diabetes, and it doesn't. It's just an accident. But in other cases, it can be two effects being caused by one particular cause. They both move together. And finally, we have the use of graphs here. These graphs are real. This is the pound-euro exchange rate from September to November 2014. And it looks as though there's a huge kind of movement in the exchange rate there. It's kind of wobbling up and down really, really quickly. But if you look here, look where it's starting. The graph is not starting at 0. The graph is actually magnifying the difference between about 1.35 and 1.42 there. If you were to draw this in the graph starting at 0, then this is what the movement looks like here. And it's a much less volatile movement in the exchange rate. It's nearly level to all intents and purposes. And finally, pictograms. What do these two sacks mean? Of money, let's say it's earnings per share or profits or anything of that sort, or employee salaries, and they might be drawn so that the height of one is kind of twice the height of the other. It might be trying to and maybe the salaries have doubled, maybe the profits have doubled, but leaving that aside, leaving the height aside, if you're looking at the sacks, what do you think they hold there? Here we've got a kind of little sack in here, kind of about the size of an apple or something. Here we've got a great big sack out here about the size of a pumpkin. And if you compare an apple to a pumpkin, you maybe automatically think of volume. This looks like a much, much bigger quantity than this. And it's because the volume of the sack increases really by the cube of the linear dimensions here. So if the linear dimensions went up by times 2, actually the volume of the sack would go up 8 times. And therefore it could be an attempt to mislead. It looks as though there's far more profits in there, far more earnings in there, 8 times when in fact maybe they're only double. So be careful when interpreting pictograms.